Hello everyone. On this video we will be going over differentials and linear approximation. Okay, so starting off we're going to look at our delta x, which we call the increment of x. Alright, so if we look at just the one-dimensional number line, let's say this is some value x, and this is some value x plus delta x. Okay, so the increment between those two values is, of course, our delta x. Okay, one way to think about it, let's say if you had 5 and 9 here. Okay, so you have 5 and 5 plus 4, so the increment would be 4. Okay, so in this case, our delta x would equal, if you want to find the difference between 9 and 5, you just subtract, 9 minus 5. So in this case, it's our x plus delta x minus x. Okay, or a higher number minus our lower number. All right. So let's look at our increment of y. Okay, so our delta y equals our increment of y. Okay, so for this one, we're going to be in 2 dimensions. Okay, so let's say this value here is x, and this value here is our x plus delta x. Okay, so let's say if we have a point here and a point there. Okay, so if this is our point here, that's our x and that's our y, then that means this value has to be your f of x, because this is the point x, f of x. And this point here, this value has to be your f of x plus delta x. Because of course, this is if you plug in x plus delta x, you will get f of x plus delta x. So let's say if we want to find the distance on the y-axis between those 2 points, that would be our delta y, or our increment of y. Okay, so we'd have to subtract this y value from this y value. So our delta y would equal f of x plus delta x minus your f of x. Alright, so what if we wanted to take that into our 3rd dimension, where our delta z is our increment of z. And give that a little more room. There we go. So we have our increment of z. Okay, so if we look at this in 3 dimensions, bring that up a little more. We have our x, our y, and our z. Okay, so let's say our x value is right there. That's our x. Let's say our y value is here. That means this point is, of course, your ordered pair of x, y. Okay. Now let's say this point here is your x plus delta x. And this point here is your y plus delta y. So you have y, go a little further down, it's y plus delta y. X, a little further down, x plus delta x. Okay, so that means this point here and this point here would of course be your x plus delta x and y plus delta y. Okay, so let's say if we had some three-dimensional object floating in space there. Okay, so that's your three-dimensional object just kind of floating in space. Three-dimensional curve. Okay, so if you have your point xy, let's say if that went up to that particular object floating around and intersected at that particular point, then this point would be your x, y, f of xy. Okay, let's say for this one, this particular point intersected the object right there. Okay, so this is your x plus delta x, y plus delta y. So that means this particular point would be x plus delta x, y plus delta y, and f of x plus delta x, y plus delta y. Okay. Now, just like above here, what if we wanted to find the increment of z? So this z value and this z value. So that increment would be your delta z. So in order to find that delta z, we would have to find f of x plus delta x, y plus delta y, minus f of xy. Okay. So delta z equals f of x plus delta x, y plus delta y, minus f of xy. So those are your increments. And we've gone over those to lead us right into our definition. Okay, so if you are still writing, feel free to press pause. But we're going to go ahead and move on to the next page. Separate papers here. There we go. Okay, so this is the definition of a total differential. Okay, so if, let's say, z equals f of xy, where delta x and delta y are increments of x and y, then the differentials of the independent variables x and y are, say, dx equals delta x, dy equals delta y, with the total differential of the dependent variable z. And that is dz equals partial derivative of z with respect to x dx plus partial derivative of z with respect to y dy. Okay. Now your partial derivative, you can change the way that looks. Remember, z is equal to f of x, so you can always call it the partial derivative of f with respect to x. And that's dx plus partial with respect to y dy. Actually, this formula is used more often than this one, but you can use either one. Okay, all depends on your particular comfort level. Okay, now this can be extended if you have more than just the two independent variables. Can be extended to several variables. Alright, so let's say that w is equal to the function with variables x, y, z, and u. Where we know that delta x equals dx, delta y equals dy, delta z equals dz, and delta u equals du. That means our dw is equal to the partial w with respect to x dx plus partial w with respect to y dy plus partial w with respect to z dz plus partial w with respect to u du. Clean that up a little bit. Okay, so no matter how many independent variables you have, you can always create a total differential formula for it. Alright, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our first example. Alright, so let's say, for example, to find the total differential for, say for problem A, if z equals 2x sine of y minus 3x squared y squared. And for problem B, w equals x squared plus y squared plus z squared. Okay, so to solve this one, partial z, problem A, find the first derivatives for x and y. Partial z with respect to x is equal to, of course, sine of y is considered a constant, so that would move to the front there. There is partial with respect to x of 2x minus, this is with respect to x, so the y squared is considered a constant, so you have 3y squared times the partial with respect to x squared. Okay, so that means that your partial of z with respect to x is equal to the derivative with respect to x is 2. So you have 2 times sine of y. Don't really need that. So you have 2 sine of y minus partial of x squared is 2x. So 2 times 3 is 6. So you have 6x times your y squared. Okay. And we need the partial z with respect to y. So in this case, the 2x are the constants. So you have 2x partial with respect to y of sine of y minus, here the 3x squared is the constant. So that's the partial with respect to y of y squared. Okay, so that means your partial z with respect to y is equal to, derivative of sine is cosine, so you have 2x cosine y minus derivative of y squared is 2y, so you have 6x squared y. Okay, so from there we know that our dz, or total differential, sorry about that, is equal to partial z with respect to x dx plus partial z with respect to y dy. Or in other words, your dz is equal to your partial z with respect to x, 2 sine y minus 6x y squared dx plus partial z with respect to y, and I'll make a bracket to keep it all uniform here, 2x cosine of y minus 6x squared y dy. Okay, and that's our differential for A. Alright, so looking at problem B, go ahead and draw a line here. Okay, you see here that w equals x squared plus y squared plus z squared. Partial of w with respect to x, you see those aren't x's, so they would just become 0. So that would be 2x. Partial of w with respect to y, that would become 0, and that would become 0, so it ends up being just 2y. Partial of w with respect to z, that would be 2z. So we know that dw equals partial of w with respect to x dx plus partial of w with respect to y dy plus partial of w with respect to z dz. Okay, so plugging everything in, our dw is equal to 2x dx plus 2y dy plus 2z dz. All right. So if you are still writing, feel free to press pause. But now we're going to look at differentiability. A definition of differentiability. Clean that up. Okay, so a function z equals f of xy is differentiable. I'll make that my differentiable at x0, y0 if delta z can be expressed as delta z equals partial with respect to x at x0, y0 delta x plus partial with respect to y at x0, y0 delta y plus epsilon 1 delta x plus epsilon 2 delta y. And really those are mostly used for any errors. So unless you're talking about a problem where they ask you about the error, you really will rarely use those. Okay, so epsilon 1 and epsilon 2 approach 0 as the point delta x, delta y approaches 0, 0. Okay, now also, just like with real vector valued functions, if f of xy is differentiable at the point x0, y0, then it's continuous at that point. Then it is continuous at x0, y0. Okay. Now be careful, because even though this is the case, the reverse is not always true. So if it's differentiable, it's continuous, but it can be continuous and not be differentiable. The reverse is not always true. All right. Okay. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to our next example. Let's say, for example, for the function f of x, y equals 9 minus x squared minus y squared. Okay, for problem A, evaluate function f at the point 1, 2 and function 1.05 and 2.1, and calculate your delta z. Okay, so for problem B, we're going to use the total differential to approximate. Our dz, or delta z, using dz. Oh, dz using delta z, sorry about that. Here we go. Alright, so we start off with problem A. You know that f of xy is 9 minus x squared minus y squared. So that means f at 1, 2 is equal to 9 minus 1 squared minus 2 squared, which is 4. Okay, so all we do is replace x with 1 and y with 2. We got our 4. Okay, so f at the point 1.05 and 2.1 is equal to 9 minus 1.05 squared minus 2.1 squared, okay, which is equal to 9 minus 1.1025 minus 4.41. So that means that the function at 1.05 and 2.1 is actually equal to 3.4875. Okay, so moving on up, we know that our delta z is equal to f of x plus delta x, y plus delta y, minus f of xy. So that means your f of x plus delta x is 1.05, 2.1, minus f at 1, 2. Okay. So what does that tell us? That tells us that the difference between x and x plus delta x, you have 1 and 1.05. So delta x equals 0.05. And y plus delta y, you have 2 and 2.1. So delta y equals 0.1. Okay, that's going to come in very handy. Okay, so that means you have 3.4875 minus 4, which means your delta z is equal to negative 0.5125. Okay, so this is your delta z. Alright, so we're going to use this to solve for our dz. Okay, so we know that z is equal to 9 minus x squared minus y squared. And our dz formula is partial z respect to x dx plus partial z respect to y dy. Okay, so if we calculate those, which we're just going to do right here on decide partial z respect to x, okay, we see here that those two terms would disappear, so you end up with negative 2x. And partial z with respect to y, see here, those two terms would disappear, so we end up with just negative 2y. Okay, so that means our dz is equal to partial with respect to x, so you have negative 2x, dx. Now remember, our dx is the same as our delta x, so our dx is equal to 0.05. So we'll save that for right now. I'll just put dx for right now, then we'll come back to that. Plus partial z with respect to y, so negative 2y dy. I don't like to jump ahead. So you have negative 2. Remember, our x value, if you go right back up, is equal to 1. Didn't have to go move that, so our x is equal to 1. So 2 times 1, our dx is our delta x, so that's 0.05. Okay, so I'm going to go over that one more time. You have your partial with respect to x, is our negative 2x. You see here that our x is equal to 1. And our dx, which is the same as our delta x, is 0.05. Okay, so we just replace those values. Okay, plus, you have negative 2. Our y is equal to 2. And our dy, which is the same as our delta y, is 0.1. Okay. That means that our dz is equal to 2 times 1 times 0.05 is negative 0.1 minus 0.4, which is equal to negative 0.5. Okay, so all those dz's and delta z's and all that comes in handy. Alright, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our tangent planes. Okay, so you have the equation of a tangent plane. Okay, so what if we let f have continuous partial derivatives? Okay, so all that means is that first with respect to x, first derivative with respect to y, first derivative with respect to z, etc. and so on, they exist. Okay, so an equation of the tangent plane to the surface z equals f of xy at the point p of x0, y0, z0 is z minus z0, which is equal to partial with respect to x at the point x0, y0 times x minus x0 plus partial with respect to y at x0, y0 times y minus y0. Okay. So this is your tangent plane approximation. Okay. Now, if we have this formula, let's say if we decide to add z sub 0 to both sides and just solve for z basically. Okay. So in other words, z is equal to z sub 0 plus partial with respect to x at x0, y0 times x minus x0 plus partial with respect to y at x0, y0 times y minus y0. Okay. And since we know that z is equal to f of xy, then that means z sub 0 is equal to f of x sub 0, y sub 0. And we also know that z is f of xy, so we have f of xy equals f of x sub 0, y sub 0 plus partial with respect to x at x sub 0, y sub 0 minus x0 plus the partial with respect to y at x sub 0, y sub 0 times y minus y sub 0. Okay? But to avoid confusion, instead of making that f of xy, we're going to make that L of xy. Just changing that first one, which is f of x0, y0, plus the partial with respect to x at x0, y0. That should be times. I don't know why I put a minus there. There we go. Times x minus x0 plus partial with respect to y at x0, y0 times y minus y0. And just tweaking that formula for the tangent plane a little bit gives us the formula for our linear approximation. All right. Okay. So if you are still writing, feel free to press pause, but we're going to go ahead and move on to our example. Okay, so let's say, for example, find the linear approximation of the function say f of xy equals x to the third times y to the fourth power at the point 1, 1. Okay, so solving this one, at the partial with respect to x, xy. Okay, remember the y to the fourth is considered a constant, so we just differentiate the x factor, so that becomes 3x squared, y to the fourth. Partial with respect to y, xy, Remember here, the x to the third is considered a constant, so we leave that alone. So we just differentiate with the 4. So that's 4y to the third. So we end up with 4x to the third, y to the third. Okay. Now we find the partial derivatives at that point. Remember, that's your x and your y. Okay. So the partial with respect to x, 0.11, is equal to 3 times 1, which is just 3. The partial with respect to y at the point 1, is 4 times 1, which is just 4. Okay. And we're also going to need to know our function value at that point, which is just 1 to the third times 1 to the fourth, which is just 1. Okay, so all three of those are necessary to find our linear approximation. Okay, so just rewriting the formula, linear approximation is equal to f of x0, y0 plus partial with respect to x at x0, y0 times x minus x0 plus partial with respect to y at x0, y0 times y minus y0. Alright, so just kind of filling everything in, our x0 and y0 is 1, 1. So that's f of 1, 1 plus f partial at 1, 1 times x minus, our x0 is of course 1, plus partial with respect to y at the point 1, 1, and y minus y0, which is of course our 1. Okay, so our function value at that point is 1, so we already got that one, 1 plus our partial with respect to x at that value is 3. We have 3 times x minus 1 plus our partial with respect to y at that value is 4. So that's 4 times y minus 1. Okay. Now sometimes they will take the answer to look like this, or they will want you to distribute, get rid of the parentheses. So you have 1 plus 3x minus 3 plus 4y minus 4. So if we combine all of our like terms, you have negative 3 minus 4 plus 1 is negative 6. So you have 3x plus 4y minus 6. So either one of those, depending on the textbook or the program, the math program, they may take the answer written as either one. Alright, so if you are still writing, feel free to press pause. I'm going to go ahead and do one more example. Okay, let's say, for example, I want to find the equation of the tangent plane for z equals 3 times x minus 1 squared plus 2 times y plus 3 squared plus 7 at the point 2, negative 2, 12. right. So, using U substitution, partial with respect to x, we see here this is a y term, so this would disappear since it would view the y as a constant. That would disappear and become 0 since 7 is a constant, derivative of a constant. Okay, so here using U substitution, bring down the 2 times U prime, which would be 1. Okay, so that's the partial with respect to x. Now the partial with respect to y. Again, using U substitution, we know if we take the derivative of this term with respect to y, it will become 0. Same with this term with respect to y, it would become 0. This one, with the u equaling y plus 3, we bring down the 2, so that would make it 4. 4 times y plus 3 times the derivative of that, which is 1. So that would be our partial with respect to y. Okay. So that means our partial with respect to x. Okay, so remember, this is our x0, this is our y0, and this is our z0. Okay, so the partial with respect to x for x0 and y0, that's just 2 and negative 2. Okay, since we only have an x, we just have to replace the x with 2. So 6 times 2 minus 1 is just 6. Okay, so a partial with respect to y at 2, negative 2. Okay, so for this one, we only have a y value to replace. We don't have any x's up here. So y equals negative 2. So we have 4 times negative 2 plus 3, which is 1. So that would just equal 4. Okay, so we have everything we need. Now we just have to plug it into the formula. We have z minus z0 is equal to the partial with respect to x, x0, y0 times x minus x0, plus the partial with respect to y, x0, y0 times y minus y0. Okay, so we can go ahead and plug everything in. Z minus z0 is just z minus 12. Equals partial with respect to x of x0, y0. Remember, that's just from your 2, negative 2. So that's partial with respect to x to negative 2. And that's x minus x0, which is 2. Sorry about the sun. I have no idea when or where it's going to pop out from behind the cloud. Okay. So plus, you have your partial with respect to y, x0, y0. That's partial with respect to y of 2, negative 2. And that's y minus y0, so that's y minus negative 2. Okay, so everything's kind of falling into place once you get your first derivatives figured out. Okay, so you have z minus 12 equals your partial at 2, negative 2. We know that's 6. We have 6 times x minus 2. Plus your partial with respect to y is 4. We have 4 times y plus 2. Okay, now in some textbooks or math programs, this would be your answer. But in others, you'd have to keep going. So you go ahead and distribute the 6 and distribute the 4. You have z minus 12 equals 6x minus 12 plus 4y plus 8. Okay, so if we add 12 to both sides, these two would disappear. So you'd end up with z equals 6x plus 4y plus 8. Okay, so like I said, depending on the textbook or the program that you're using. Either one of those would be the answer, depending on how they wanted it to be presented. All right. So hopefully all of this made sense, and I will see you on the next video.